So conditioning. Conditioning is the property of a problem. Okay. For example, if I give you a problem that given an input x, you are calculating some f of x. This problem, so to speak, how good is this? Is it even solvable? Things like that. What does this mean? This means, for example, if I want to give you two lines like this, and I wanted you to find the intersection point of the line, given the slope and intercept of this line and the slope and intercept of this line. I say this problem is ill-conditioned. Why do I say that? For example, if my m1, the slope of my first line, changes by just a little bit, such that my new line becomes this. My slope changed just a little bit, and you can see the point of intersection moved quite a lot. Quite a lot. Quite a lot in quotes. In contrast to that, if I had a pair of lines like this, M1, C1, M2, C2, if I change my slope of, let's say, line M2 this time by just a little bit, my point of intersection moved a little bit in quotes, which I don't know what do I mean by big and small, that will be something that will go on now. But this is the idea. So for example, let's say I have my point x in my space, which is mapped to f of x in space. This is in some d dimension, this is in some k dimension, whatever. Now my question is, for a set around my x, let's say a ball around my point x, my function maps it to another ball in this dimension, let's say, around f of x, right? For example, this point, let's say point alpha, will be mapped to f of alpha. My point x is mapped to f of x. So the question that I want to ask is, what is this size comparison between these two sets? So for example, this is how we define the absolute, this is how we would define the absolute error of an algorithm. For example, if my input is x, but my let's say little perturbation leads to x tilde, my function goes from f of x to f of x tilde, right? So the absolute error in my function is f of x tilde minus f of x, absolute value. So the condition number is defined as such: k absolute is the supremum of f of x tilde minus f of x divided by x tilde minus x, absolute value, in the limit x tilde tends to x. This is how my absolute condition number is defined. Now, what is relative error? Relative error for my function is like percentages, let's say. So relative error will become f of x tilde minus f of x divided by f of x, something like that. So my relative condition number, k relative, is limit x tilde tending to x, f of x tilde minus f of x divided by f of x. This whole thing divided by the relative error in my input, which becomes x tilde minus x divided by x. Multiply this. Yeah. So I mean I wanted to divide the percentage error in my output by the percentage error in my input. So this is how it looks. This is the relative error of my, this is the relative condition number of my problem. So this gives us a window. This gives us an opportunity to understand if this problem is nicely conditioned, if this problem is even worth solving. For example, if my condition number is a lot, is quite a high number, what that means is as x tilde tends to x, this number becomes smaller, but this does not become smaller with the same rate, which means that for example, this problem, for example, this will be an ill-conditioned problem. Even if my x tilde tends to x, my m2, my slope of m1 perturbation goes to m1, my point moves quite a lot. So it's an ill-conditioned problem. So the point that I'm trying to make is, if a problem is ill-conditioned, if the problem is badly conditioned, no matter how much computational effort you throw into that problem, your results will not be accurate enough. So condition number is the property of a problem, not a property of an algorithm. If the condition number of a problem is bad, do we even bother solving that problem? These are the questions that one can answer if he knows. So what do I mean by condition number big? Condition number big and condition number small, well conditioned, ill conditioned. This depends on the problem that you're trying to solve. What is the condition number that you can tolerate on your system, on your desired precision, and it's the algorithm designer's call. However, just a heuristic, if condition number is 1, let's say condition number is 1, it is a good condition problem. I mean, because your fx scales as much as your x, to be honest. The size of this ball is same as the size of this ball. It's a nicely conditioned problem. If my x moves a little bit, my fx will move by the same proportion. Similarly, a k relative of 1 a condition number of 1 can be considered as a good condition number. That's just a heuristic I'm throwing out there. But in the end, it depends on the problem that you're trying to solve. So that's the property of a problem, the condition number. I see how to quantify a condition number. Now we move on to, let's say, linear systems, for example. I have this problem, ax equals to b, right? My function looks like this. F of x, x, and then f of x maps my x to another A inverse b. I take the input as x and my output is A inverse b. That's what my function does. This is what my linear system solver does, right? We have to see how well conditioned this is. Well, this function f of x going from x to A inverse b, this function has two parameters, a and b. So we have to see what's the condition number of this problem with respect to these two parameters. For example, one thing that I would like to add, if my function is differentiable in this domain, in this neighborhood, in this ball, let's say, then my relative condition number becomes, as you can see, there is something going on here. Fx tilde minus fx divided by x tilde minus x, and x tilde tending to x. So my condition number becomes f prime of x times the x divided by f of x. And if my function is again differentiable, then my absolute condition number is also f prime of x. Now this gives us a nice definition to understand. For example, if this is my function, if I just plot a function randomly with respect to x, if my x moves a little bit, how much will my f move? Instead, if my function was something like this, let's say a tan function, if my x moves by a little bit, how much does my f move basically? This is the definition of the absolute condition number, and to an extension, the relative condition number of a problem. Right? Now again, all of these condition numbers are defined with respect to the norm which you're going to take. It can be a 1 norm, it can be a 2 norm, it can be an infinite norm, things like that. These are really dependent on the norm which you are going to use to analyze your function. For example, we look at this function f of so for example, we look at this function. F is a function which goes from R2 to R. It takes A and B as input and outputs A plus B. Right? This is my function. This is basically just addition of two numbers, right? This is just an addition of two numbers. So now we'll understand the condition number of this problem. Before I move forward, I want to also talk about this particular number. Let's say I have norm of f prime x. Right? Now, for a function, for a general function, let's say going from Rn to Rm, f prime is a Jacobian matrix. F prime is a matrix of dimension m cross n, right? What does it mean for a norm of a matrix? The norm of a matrix is an induced norm. What that means is a norm of a matrix A is equals to Ax divided by x and the supremum of this, of all x over all x. The maximum value of Ax divided by x, and also the fact that this is not zero basically. This is how we define the norm of a matrix. We can also define it in such a way: supremum of Ax given norm of x is equal to 1. Basically just remove the denominator, that pretty much. So that's how you define the norm of a matrix. So now if we move on to, let's say, a problem of finding out the condition number of addition, let's say. So I have a function which maps from R2 to R, takes the input A, B and outputs A plus B. So it has a two-dimensional input and 1D output. So what is my f prime? My f prime will be, f prime with this respect to this will be first differentiate with respect to A, it is 1, then differentiate with respect to B, it is 1. So this is my f prime basically. 1, 1, it's a 1 cross 2 vector. Now how would I define its condition number, absolute condition number? Absolute condition number, like I said, it's a differentiable function. I'm gonna keep that. The absolute condition number is the norm of the derivative, right? So it's the norm of f prime, or let's say the norm of 1, 1. This is my absolute condition number. Now how do I define the norm? I define the norm as this. So let's plug the definition in. The norm of this will be, let's say I take another x of size 2 cross 1 such that this x is x1, x2. Alright, so my k absolute is this multiplied by x, this becomes x1 plus x2 divided by the norm of x, right? Why did I write this? This was my f prime, right? 1 cross 2. I just multiplied f prime with this. So norm of f prime is equals to f prime times x divided by the norm of x, right? The norm of f prime times x divided by the norm of x, and f prime times x will be just x1 times x2, x1 plus x2. That's what it's over there. So now, if I take my, let's say, if I take my one norm, let me just take one norm. This becomes mod x1 plus x2 divided by mod x1 plus mod x2. If both of my numbers are positive, this is 1. This is a condition number of 1, which means that this problem is well conditioned. That's what we mean. That's what we mean. Addition is well conditioned, subtraction is not well conditioned. That's the pretty much. There's nothing more to it. This is how the norm of a matrix is defined. I'll call it the induced norm. Matrix induced norm. Right? Next is we are going to talk about condition of a matrix. For example, we always come across this thing, Ax equals to B. We can come across this for quite many applications, to be honest. So this problem is mapping Well, it's taking x and returning the answer A inverse B. A inverse B. Taking x and giving the answer A inverse B. So next we're going to discuss about Ax equals to B, this problem. Linear systems or linear least squares for that matter. I am given A, I am given B. This is my function. It takes an A, it takes a B, and it returns A inverse B. This is a function of two inputs, right? So we can analyze its condition number based on, let's say, the two inputs separately. For example, let's keep A fixed and let's see how much does my output change with respect to perturbations in B. So the absolute condition number is K absolute is the derivative of this, the derivative of my function with respect to B, which is just the norm of A inverse, right? The norm of derivative, which is just the norm of A inverse. This is like differentiable with respect to B. What about the relative condition number? The relative condition number is going to be, as we defined it, as it's differentiable, we write this relative condition number as norm of B divided by norm of A inverse B, times the norm of A inverse. This is how we would write our relative condition number, right? Now, using the, yes, I will write B as AX, the norm of AX divided by the norm of X times the norm of A inverse. Using the Cauchy-Schwarz inequality, I can separate them. Norm of A and the norm of X divided by the norm of X times the norm of A inverse is equals to this, A inverse. That number is the relative condition number with respect to B. Now, as it turns out, if I were to calculate this again, the relative condition number with respect to perturbations in A, I will get the same answer there. I will get the same answer. So it turns out, and it's not only this problem, this number comes up in a lot of scenarios. So I will define condition number of a matrix A as A times A inverse. Alright? Times A inverse. This is how I define the condition number of a matrix A. There are also other definitions, which is the maximum of AX divided by the minimum of AX. For a symmetric matrix, I think. For a normal matrix, this becomes the maximum eigenvalue divided by the min eigenvalue. For a general matrix, this becomes the maximum singular value divided by the minimum singular value. So, keeping this in mind, this is the condition number of a matrix. This is like an important definition, the condition number of a matrix. Okay? Now we move from analysis of the problem to analysis of the algorithm, the stability of an algorithm. This is what we are going to talk about next. For example, if I have an input set, if I have, let's say, an input set X, and my function maps it to f of x. Well, this is just one point I'm talking about, x to f of x. This is my, let's say, E set E of all the numbers around x, it maps to, let's say, set R, all the numbers around f of x. So I'm going to construct a diagram here. Input error, errors in the algorithm, errors in algo result in output errors. This is just a way of showing. Input errors is something that we cannot do about, something that we can't do anything about. It comes from the input, it has to stay in the input. We can't change that. Error in algorithm, now that's something that we can analyze. That's where the stability of the algorithm as a discussion comes in. So, what does stability of the algorithm mean? The stability of the algorithm means if, let's say, I had a function f, this is like the true, absolute true image of f. What if instead of f I had, let's say, another function f tilde, which is something that's implemented in my computer, it's prone to rounding off errors and such things like that. This is gonna map my set E to a bigger set R prime. Because it's prone to errors, it's always going to contain this set, but then it's also going to contain more numbers, a more number of possibilities of answers that this algorithm can give because it's prone to errors. So this is what the stability analysis is going to be. If x maps to f of x, but then my perturbed function f tilde x, the function implemented in my computer, maps x to another point f tilde x, I want to know how big of a difference this is. I want to somehow be able to compare how much f tilde x is far from f of x, right? So yeah, I mean, using the same thing, like the relative error, basically f tilde x minus f of x divided by f of x is some way of quantifying this error. So basically this is what I mean. The forward error is what I am trying to quantify. There's another way of analyzing the function, which is called as backwards analysis. Backwards analysis looks something like this. Instead of seeing how my f tilde projects x onto another image, into the image, what I'm going to do is I'm going to find another point x f of x. Okay, now what my function does is, my function is, let's say, it's a perturbed function f tilde. It maps here f tilde x somewhere here, right? F tilde x. What I want to do now is I want to understand what could have been my actual point x hat for which my f would be the same. For example, basically what I want to do is I'm going to write here f tilde of x is f of x hat. What could have been the input x hat for which my function would give the same answer, f tilde x? My true function would give the same answer. So f of x, which is my true function, f of x hat is f tilde of x. Now I want to know the error between x and x hat, basically. So the question that I'm going to ask is, if I had an error here, if I propagate it backwards towards the input, how much is my input error which reflects here as an output error? In the case of forward analysis, what we did was directly analyze the output errors. Here they are going to analyze the error in the input that could have caused such an error in the output. Basically, that's what backward analysis is. So that's a stability concept. Now, if let's say my these errors are tolerable with respect to my application of the problem. For example, if let's say my input errors in case of a backward analysis is of the machine precision of, let's say, 10 to the minus 16 or those sort, I'll say my algorithm is stable because my input errors are bounded by a number. So this is just a way of analyzing your algorithm, and this truly depends on the implementation and how much error you are willing to tolerate and things like that.